Lighthouse Scientific Education presents a lecture in the Atomic Structure series. The topic, Trends in the Periodic Table. Material in this lecture builds upon the previous lectures, Electronic Configuration, and Valence Electrons, Octet Rule, and Dot Structure. Trends in the Periodic Table. We will first familiarize ourselves with how general trends can be viewed upon the periodic table. We will outline the basic factors that drive these trends, and that includes effective nuclear charge. Specifically, we will look at atom size using radius, ionization energy, electron affinity, electronegativity, and ion radius. A note before we start. While it is always a good idea to keep a copy of the periodic table of elements around when doing chemistry, for this lecture, it is a must. Make sure you have one before proceeding. General periodic trends. And we begin with a little disclaimer. The trends covered in this lecture are considered general because there are some exceptions to the stated trends. Understanding why some elements are exceptions can be found with a deeper look at their electronic configuration. Fortunately, or unfortunately, depending on your view, most students will not be asked to dig into the electronic configurations for the rationale of untrend-like behavior. It is much more important to have an understanding as to which way the trends go and what are the underlying principles guiding those trends. For instance, why do atomic radii, plural radius, decrease when going across a row on the periodic table of elements? Why is the energy cost of losing an electron less for sodium than it is for chlorine? Conversely, why is the allure for gaining an electron greater for chlorine than sodium? What drives sharing electron? That's electronegativity. And if an atom gains or loses an electron, what should we expect to happen to the radius of the corresponding ion? We can ask these questions in the context of the organization of the periodic table. We will ask, how do these properties or trends change going down a column or group? Are these trends similar for all columns in the table? What about going across the row or period? Are these trends similar for all rows? The answer to these questions lie in the basic principles of the atom. Factors that explain trends. We will use this cartoon of the periodic table to overlay the direction of trends. Note that it is colored by orbital blocks. Of fundamental importance to understanding periodic trends is that negatively charged electrons are attracted to the positively charged nucleus. And electrons in an atom repel each other. That's even true for paired electrons in an orbital, though having opposite spin really helps. Remember that moving down the table or down a group increases the number of shells. That's the principal number n. N equals 1, then n equals 2, n equals 3, and so on. The larger the shell, the bigger the orbitals. Pictured here are 3 s orbitals corresponding to n equals 1, 2, and 3. The orbitals are nested. One s is in 2s, and both of those are in 3s. The atoms with only 1s and 2s orbitals are smaller than those with a 3s orbital. The logical conclusion, more shells means bigger atom. And what's so important about being bigger? Well, the further an electron is away from the nucleus, the weaker it is held. Since the outermost electrons are the ones that are going to be gained, lost, or shared, how tightly held they are is going to play a big role. But why are those electrons furthest away from the nucleus, not as tightly held? There are two main answers. The first one is distance dependency. And that is that the further away opposite charges are from each other, the weaker the attraction. An analogy would be bringing two magnets together. It is only when they are close to each other that we feel them draw each other strongly. Move them apart, and the attraction decreases. In an atom, the outer shell electrons are furthest from the nucleus, and therefore have less overall attraction. The second reason is electron shielding. Electrons in the inner shells shield electrons in the outermost shell from some of the nuclear charge, the positive charge. Consider this diagram of an atom that has two inner shells which are full of electrons. The nucleus, we will say, has a charge of Z, where Z is the number of protons. Z is also the atomic number. This atom also has one outer shell, and that is not completely full. The electrons in shell n equals 1 and n equals 2 are closer to the positively charged nucleus and hide or obscure or shield some of that positive charge, such that the outer shell electrons feel less than the full nuclear charge. What remains to attract the outer shell electrons is the effective nuclear charge, ZEFF. And that is defined as part of the full nuclear charge that remains after the shielding and is capable of attracting the outer shell electrons. So, the closer an electron is to the nucleus, the more the effective nuclear charge resembles the whole nuclear charge. Strong attraction. And the further away an electron is from the nucleus, the more shielding there is, and the smaller the effective nuclear charge is compared to the whole nuclear charge. Weaker attraction. Bottom line, further away and with less nuclear charge attraction, the outer shell electron is less tightly held. We can use these factors to explain some of the non-intuitive trends of atomic size, specifically the atomic radius. Giving some perspective on the radii of atoms, small atoms like hydrogen have radii in the order of 0.3 angstroms. Larger ones like cesium are in the order of 3 angstroms. And in case you are new to the angstrom, 1 angstrom equals 10 to the minus 10 meters. Pretty small. To the trends. Atomic radii increases going down a group or a column. Why is that? Moving down the table increases the number of shells. And as we've seen, the larger the shell, the bigger the orbitals. Bigger orbitals mean bigger atoms. As for going across the row or period, atomic radii decreases. This may contradict the argument we just made for explaining larger atoms when moving down a column, but a closer look will reveal a more complex situation. First of all, moving across the row increases the atomic number and therefore the number of protons. More protons means a more positively charged nucleus. But in contrast to going down a column, in going across the row, electrons are added to the same shell, like to the 2s and then 2p. They are not added to a bigger shell. The effect is that the higher positive charge draws in orbitals and shells, resulting in smaller radii. A demonstration will help make this point. We will start with a model of the atom based on the octet rule. Up to 2 electrons in the first shell, 8 in the second, and up to 8 in the third. Our demonstration has 10 electrons, 2 in the first shell, 8 in the second. It is neon. We're going to take a cartoon look at what happens to the size of the atom as we move along, element by element, of row 3 of the periodic table. As we go along, we will keep track of the number of protons and electrons of each atom, as well as the nuclear charge Z, even though that is going to be equal to the number of protons. We should become more comfortable using Z as a charge of the nucleus. The first element of row 3 is sodium. It has 11 protons and electrons. The 11th electron is added to a new shell and equals 3. The larger radius is consistent with the argument of increasing radius going down the table row by row. Moving to the next element, magnesium, its 12th electron is added to the same shell as the 11th electron. However, magnesium, compared to sodium, has a larger nuclear charge, and that larger positive charge has the effect of drawing all the electrons a little closer to the nucleus. The result is a smaller atom. Element 13 is aluminum, and its 13th electron is added to the same shell as the 11th and 12th. The larger nuclear charge creates a larger attraction for negatively charged electrons in corresponding shells, and orbits contract. Same argument can be made for the 14th electron of silicon, as it is when pairing phosphorus's 15th electron, sulfur's 16th electron, chlorine's 17th, and argon's 18th. They all follow the pattern of decreasing atomic radius when the electron or the last electron is added to the same shell. The periodic table is a good platform for showing periodic trends. For instance, the atomic size of atoms in column 1 increases going down the table. We could read out the elements of this column from top to bottom, hydrogen to cesium and finishing with francium, and each element we call out would be larger than the previous one. Another way textbooks show trends is by graphing. Graphs have the advantage of being visual, and as the old saying goes, a picture is worth 1,000 words. Here's a graph of the first 86 elements plotted by their atomic number and atomic radius. On the x-axis are the atomic number of the elements. We can treat the x-axis as listing out the elements one by one, starting with hydrogen and ending with the 86th element, radon. Above each atomic number is plotted that element's atomic radius. To help us discern the same trends we previously covered, we can label the points on the graph that correspond to the elements of the first column, hydrogen to cesium. We can see the trend of increasing radius going down the column. On the graph, going down the column is going left to right along the atomic number axis. And what about the other trend? It says that the atomic radii decrease going across the row, such as going from hydrogen to helium, or really any column 1 element and moving across the table to the noble gas at the end of the row. Returning to our graph, we can see the same trend beginning with a first column element and decreasing going along a row. Row 1, starting with the atomic radii of hydrogen and decreasing to helium. Going down a row, starting at lithium and decreasing to the last element of the row, neon. Starting with sodium and decreasing atomic radii to argon. Next, potassium to krypton. Rubidium to xenon. And finally, the column 1 element cesium to the atomic radius of the noble gas radon. Both trends are apparent using a handful of labeled points and a bit of practice reading graphs. And yes, there are exceptions to the trend, but for atomic radii, they only occur with larger atoms. On to our next periodic trend, ionization energy, or IE, which is the energy necessary to remove an outer shell electron from a gaseous atom. The general formula is some atom X gives up an electron and becomes an ion. The subscript G indicates that the atom or ion is in the gas state. Note that the ion X has a +1 charge, since it now has more protons than electrons. To be complete, we might add an energy term to the reactant side of the equation, and that energy would be the ionization energy. It is reasonable to suppose that the more stable an atom type is, the larger the energy will be needed to remove an electron. Since the IE is on the reactant side of the equation, it can be treated like a cost. Therefore, large ionization energies are large costs and will have the effect of lowering the likelihood that such a reaction will occur. It can just be too expensive. Keep that point in mind. From a cartoon perspective, an example of ionization has an atom struck by some sufficient amount of energy that knocks off one of the outer shell electrons. The atom becomes a cation, and as we will see later in the lecture, with one less electron, the radius of the ion is less than the radius of the atom. Another example is where a full atom has 2 electrons knocked off. The atom is struck by some sufficient amount of energy. An electron is knocked off, making the atom into a cation. A second and larger amount of energy knocks off a second electron. The +1 charge becomes +2, and the radius of the +2 ion is even smaller than that of the +1 ion. That amount of energy needed to knock off the first electron is called the first ionization energy, and the second amount of energy is called the second ionization energy. The second IE is always larger than the first, because it is harder to remove an electron from a cation, +1, than from a neutral atom. Even more electrons can be knocked off, but it requires larger energies to remove successive electrons, because the negative charge electrons are being taken off an increasingly positively charged cation. We will, however, only concern ourselves with the first ionization energy. As for trends, moving down the table or column, the ionization energy will generally decrease. We can reason this out by noting that the larger the shell, the bigger the orbitals, and bigger orbitals, the outer electrons are further away from the nucleus. That means more electron shielding, translating into a lower effective nuclear charge. The outcome being outer shell electrons that are weaker held and therefore need less energy to knock them off the atom. Moving across the row on the table, left to right, the ionization energy increases. The reason here is that there is an increase in the number of protons when moving across the row, creating a larger nuclear charge Z. And as we saw earlier, that results in decreasing radii. As such, the outer shell electrons are closer in to a more positive nucleus and will therefore require a larger amount of energy to break them away from the nucleus. It's all about charge-charge interaction. The stronger the attraction of an electron is to the nucleus, be that by proximity or by effective nuclear charge, the more energy that will be needed to overcome that attraction and remove that electron. We can combine what we know about ions and the IE trends to the periodic table. Let's ask a couple basic questions. Which column has the most stable elements and should therefore require the largest ionization energy to remove an electron? Yeah, the noble gases. They have stable electronic configurations and do not want to give up that stability by losing an electron. Second question. Which column contains atoms that are most likely to become positive ions? Consider the cations that we've come across already in our studies. There are the alkalis of column 1. Sodium and potassium become +1 ions, generating electronic configurations of their nearest noble gas. And then the alkalines of column 2, magnesium and calcium lose 2 electrons, forming +2 ions, generating electronic configurations of their nearest noble gas. It is reasonable to suppose that they have relatively low ionization energies, since they readily undergo ionization and end up with more stable electronic configurations. A graph plotting atomic number versus IE should bear that out. As argued, the noble gases should have the highest ionization energies in their row. Using the noble gases as a representative group, the trend for IE is decreasing going down a column. The IE decreases going from helium to radon. The other trend was increasing across the row. That is low IE for the column 1 elements to high IE for the noble gases. Row 1. Hydrogen's IE increases to helium's IE. Row 2. A low IE for lithium to a high IE for neon. Sodium to argon. Then potassium to krypton. Rubidium to xenon. And finally, row 6, the first column element cesium to the noble gas radon. There are some deviations, beginning in the 4th row. Note that the lowest IEs are the column 1 elements, and just a bit higher are the column 2 elements. Our reasoning based on stability and familiarity of common ions is borne out. Our next trend is electron affinity, or liking for, EA for short. EA is really the opposite of IE. It is the energy released when adding an electron to a gaseous atom. The general formula has some atom X accepting the electron and becoming a negatively charged anion. The anion has one more electron than proton, producing a -1 charge. If we were keeping track of energy, we would include the release of energy as a product of the reaction. Since the EA is on the product side, we can treat it like a profit. Therefore, the larger the release of energy, the bigger the profit, and the more likely the reaction will occur. Comparing the IE and EA, larger ionization energies are like large costs, and large electron affinities are like large profits. We can visualize electron affinity with this transfer an electron when 2 atoms come together. One of the electrons of the atom on the right is transferred to the atom on the left. The lossy electron produces a cation, which adopts a smaller radius. The gain of an electron by the atom on the left produces an anion with a larger radius. More on ionic radii later. The trend moving down the periodic table, or group, is that EA generally decreases. As argued before, moving down brings about larger atoms. Larger atoms means the further an outer shell electron is away from the nucleus. And that leads to more electronic shielding, producing a lower effective nuclear charge. The result is less positive charge to attract a more distant electron. Moving across the table, left to right, there is an increase in the EA. As mentioned previously, moving right across the row increases the number of protons. Z, the nuclear charge, becomes larger. Also, when moving right, the radii decreases, and the outer shell is closer to the nucleus. An added electron will therefore be closer to the nucleus. The combination of stronger nuclear charge and being closer to the nucleus means that there is more positive charge to attract and keep a closer electron. It should be noted that the noble gases do not follow the trend. Again, they are stable with a full octet and are reluctant to add more electrons. Returning to the trends using the table, decreasing going down and increasing going across. Why don't we ask the same type of questions we asked with the ionization energy? Which column is the most stable and should therefore release the least amount of energy when an electron is added? Again, it is the noble gases. In fact, these elements are so unlikely to gain an electron that most graphs or tables of electron affinity don't even bother to include them. The second question relies on our understanding of negative ions. Which column contains atoms that are most likely to become anions? That would be the halides, chlorine and fluorine, and to a lesser extent, the chalcogens, oxygen, sulfur. If these columns of elements readily accept electrons, then we should expect such reactions to produce large releases of energy, bigger profits. Does a graph of atomic number versus electron affinity support these assertions? If we label the halogens, we see that the elements do produce highest releases of energy when gaining an electron. Again, noble gases are omitted from the graph. If we label the chalcogens, we see the second highest release of energy per row. Using these two columns of elements, we see the downward trend in EA with increasing atomic number, going down a column. Already we note exceptions with row 2 elements, oxygen and fluorine. As to the trends of increasing EA going across the row, we see a low electron affinity with column 1 lithium, rising to a large EA with fluorine. Same pattern crossing the table from sodium to chlorine, potassium to bromine, rubidium to iodide. There's a fair amount of non-trend behavior with the heavier D block elements. All right, so far we've looked at the periodic trend in losing and gaining electrons. Now it's time to look at how well elements share electrons. That's called electronegativity, or EN, and it is the capacity of an atom in a molecule to attract shared electrons from another atom. Sharing electrons in a molecule is itself an important topic and is covered later in covalent bonding. For now, we'll just say that some atoms can and do share electrons. The thing is that sharing is difficult to actually measure. So scientists have derived artificial scales that give relative strengths, relative as compared to other atom types. The most common scale used in chemistry textbooks is the Pauling scale. First of all, noble gases are generally not included. We saw the same thing with electron affinity. The Pauling scale goes from 0.8 to 4.0. The periodic trends for electronegativity are similar to those of electron affinity. Since electronegativity is about sharing, it's not surprising that affinity, or liking for an electron, is an important feature of electronegativity. We could therefore make similar arguments for the trends, and that includes decrease going down a column and increasing going across a row. As with electron affinity, the halogens are the column to watch. Looking at a graph of atomic number versus electronegativity shows a pattern similar to electron affinity. The scale, as mentioned, goes from 0.8, about 1, to 4. Using the halogens as our example for going down a column, we indeed see that electronegativity decreases. Going across a row, such as row 2, lithium to fluorine, finds the trend increasing, and that plays out for rows 3, 4, 5, and row 6. There are, of course, exceptions, which at a closer look at the electronic configuration should help explain. Electronegativity is an essential tool in broadening one's understanding of chemistry. It will follow the chemistry student as far as they choose to go in this field. Our last trend is that of ion radius. An understanding of ionization energy and electron affinity is useful in explaining why some atoms lose or gain electrons. Combining that understanding with the octet rule will further explain how ionization affects the size of the atom or ion. Remember, the octet rule says atoms interact with other atoms such that each has 8 valence electrons, like their nearest noble gas. The pattern of the first 3 shells is 2, 8, 8. Appropriate to this discussion, one way to obtain an octet is to gain or lose electrons, forming ions. We're going to revisit the model of the transfer of an electron between atoms, but in the context of ionization energy, electron affinity, and the octet rule. Sodium, with its 11 electrons and protons, will stand in for the atom type that loses an electron. Looking at the electron distribution, we see it has 2 electrons in the first shell, 8 in the second, and a lone electron in the third shell. It's on the right side of the atom for demonstration purposes. Sodium has a low ionization energy, which means that there is a smallish cost to giving up that outer shell electron. Chlorine, with its 17 electrons and protons, will play the part of the type of atom that gains an electron. Looking at its electron distribution, it too has 2 electrons in the first shell and 8 in the second. But it has 7 electrons in the third shell. Chlorine has a high electron affinity. Gaining an electron will yield a high energy or profit. That's because its third shell only needs 1 more electron to be complete and adopt a noble gas electronic configuration. It can complete that shell by acquiring the lone third shell electron of sodium. Now, the 11 proton sodium atom has become a +1 sodium ion. It only has 10 electrons, 2 plus 8, just like the noble gas neon. And since the third shell is no longer occupied, it is not considered part of the radius. The 17 proton chlorine atom has added an electron and become a -1 chloride ion. Yes, there is a name change in going from atom to negative ion, but this is also a topic for later discussion. Chloride has the 2-8-8 electron arrangement like its nearest noble gas, argon. However, with that extra electron, chloride has more negative charge than it has positive charge in its nucleus. It's reasonable to suppose that a 17 proton nucleus could not attract 18 electrons as well as it did 17 electrons. The radius of the ion should therefore be larger. The take-home lesson is that positively charged cations have a smaller radius than their counterpart atoms, and negatively charged anions have a larger radius. A final note, using the analogy of ionization energy as costs in a reaction and electron affinity as profits, the type of electron transferred pictured here is only likely to occur if the costs are less than the profits. Recapping the lecture. We introduced effective nuclear charge. That is, part of the full nuclear charge that remains after shielding. The results being outer shell electrons are less tightly held. For periodic trends, atomic radius increases going down a group or column. The cause is that going down the table increases the number of shells. Bigger shells have bigger atomic orbitals, leading to bigger atoms. The trickiest trend that we came across is that atomic radius decreases going across the period or row. We noted that going across the table is increasing the number of protons, and that the subsequent addition of electrons is to the same shell, such as the same S&P. Higher nuclear charge pulls the orbitals in, causing smaller radii. Next was ionization energy, IE, the energy necessary to remove an outer shell electron from a gaseous atom. Moving down a column or group, the IE generally decreases. That's explained by noting that the further an electron is away from the nucleus, the weaker it is held. Think lower effective nuclear charge. Bottom line, less energy needed to remove it. Moving across a row increases the IE. Moving across increases the number of protons, resulting in a decreasing radius, and the closer an electron is to the nucleus, the tighter it is held. More energy is needed to remove it. The electron affinity, EA, is the energy released due to adding an electron to a gaseous atom. Its periodic trends include a general decrease moving down a group. The further an electron is away from the nucleus, the weaker it is attracted, low EA. And moving across the row, the EA generally increases. We saw that the radius decreases moving across the row, and the closer an electron is to the nucleus, the stronger it is attracted and accepted, higher EA. The electronegativity is a relative scale that calculates the capacity of an atom in a molecule to attract shared electrons from another atom. And the trends are similar to those we found with electron affinity. And finally, the ionic radius. We saw that cations have a smaller radius than the corresponding atoms, while the anions have a larger radius. And that concludes our lecture. Trends can be memorized or they can be derived if one learns the foundation properties.